Alrighty, happy Tuesday. Hope you're staying warm. First order of business, very exciting. We have a pre-test. They gave it to me late, and I forgot to tell you on Thursday, because Thursday was crazy. But that's okay. So, it's like a couple questions. Download the Word doc. Please don't write this by hand. It's terrible. I don't want to read your handwriting. Um, just type it in right here. It's fine. So you just write a couple bits of code here for these 5 questions. 1, 2, 3, 3, 4. It's not mine. They gave it to me. So sure. Um, as part of our accreditation process, we assess prior knowledge coming into classes here. It's very exciting. So take a minute, get that done at some point. I put a due date of next week at some point. Um, it should go pretty quick. So get that done at some point for me, if you would. And then I did post a quiz, the first one here for the chapter 2 stuff that we covered. So that one's due Thursday, 11:59 p.m. I've got the other quizzes here. I did copy pasta from last time. Very exciting. So I should remember to turn them on every Thursday, sort of our sequence here. We do the following Thursday. Uh, Again, the goal of these is to get you to read the book. That's why I give them. So hopefully you'll actually read some of the text. Um, they're open book, open notes. They're not timed, so they should be free points if you go and read the textbook. Is the idea with those for the quizzes. So I'll turn those on as we go. Um, and then we're skipping chapter 3. I'm going to briefly talk about chapter 3, but we don't need to spend a whole lot of time on it here. We'll get into chapter 4, recursion. We just need to talk about a few of the highlights from chapter 3 is the analysis piece. You'll dive super deep into that in 350, your data structures and algorithms analysis course. So we just kind of intro the topic. You can get in deep and learn all the actual terminology and notation and stuff like that for it. Um, Really, what we care about here, and we're going to start to look at efficiency of our algorithms. How fast do things run? That's the time complexity, and how much memory they use while they're running. We call that the space complexity. So the more n things you have, usually the longer it takes, so the more space it takes up. And there's trade-offs of different ways of storing data that we'll look at. Some are faster at some things and slower at other things. Okay, so that's the 30-second overview of chapter 3. And we'll get more into that as we go with some of these things. We're going to talk about recursion this week. It's one of my favorite topics here. Now, when we talk about recursion, it's a wonderful tool for very specific use cases. It's not an everything tool, kind of like inheritance. It's not your everything tool, right? And you can use it for certain places where it makes sense to use. Same with recursion, right? Sometimes it's really nice, really helpful, really easy, and it makes life easy for us because we don't have to manage all of the other things. Technically, anything we can do with recursion, we can do without recursion, but it just saves us a bunch of steps. So we'll look at a couple examples of that here, why it's easier for us to use recursion than trying to manage it without. And in general, it actually performs worse than doing it iteratively because it has to manage all these other things behind the scenes. It's just nice for us. Okay, so we'll get into that, and then we'll go from there. Okay. All right. Oh, I wanted to talk about the lab. So I did have a nicer version here. So a couple people had asked me questions here, and I was like, "Oh, just call next." That's a little bit ugly here, but essentially, once you make your progression here, the way that this iter thing works, it means you can iterate over it. You can put it in a for loop, and you can get the next value and get the next value and get the next value. So instead of calling next every time here, if you just go get the value here, so it's for value in that progression here, this will automatically call the next for you automatically. You just have to go then break your loop at some point, which I generally think breaks are ugly, but I think this is probably fine. Or you could put that also in, like, I don't know. There's a couple ways of going about it here, but this is probably fine. So our geometric progression has the R value, has the start value, right? Our expected sum is the start value divided by 1 minus R. And then we just go until we get close enough. Right, whatever this millionth is here, I don't actually count the zeros here. We'll print out what that sum is. So if we run it here and say, hey, let's start with 0.5 here, and if we start with 2, right? So 2 divided by half should be 4. Eventually we get up to 4. It's 2 plus 1 plus a half plus a quarter plus an eighth plus a 16th plus on and on and on and on. We'll get close enough to 4 where we can call it, it's pretty much 4, right? and then you just see all those steps as you go here. So the idea with the Fibonacci sequence here, we just want to go get the first 500 values of the Fibonacci sequence, and then there's lots of cool things we could do to get the leading digit. The cheap, easy way here is just turn it into a string and take character 0. That's probably the fast way. I'm all about fast things because it's only 500 digits. It's not like we're doing this for a zillion times where we care about performance. 500 operations, like that. It's not a big deal here. So we would make a new Fibonacci sequence here. So fib, the Fibonacci progression, and then we want to go have some values then as a list, and for value in fib, let's take values dot append the fib value, and then we probably need a count here. So 0, we'll take count plus equals 1, and if count is greater than or equal to 500, break. Right? Just this way we don't have to call the next. You could put this in a while loop, and you can call fib.next. That's a little bit uglier here, not quite idiomatic, and again, we're not supposed to call those private helper functions, but it's not the end of the world here, right? And then really we want this as a string here, so we take this as a string, and then if we want just the leading digit here, we can take the index 0 of that string as we go here. Right, so that's our digits, maybe. It's probably better to call it digits here, right? And then we can print out our digits, and we should have a nice little list. One. Oops, that was no good. Can't have an R value of 1. That'll never end. 0.5, 1. Nope. What did I do wrong here? String of fib. Oh, we need the next value. Shoot. Can't take the string of it right away. Hang on. So value. Oh, goodness. Number is fib. Take the string of number. Just when I'm converting, it's giving me this is the class name here right away. Let's try that. Try the one. No? Oh my goodness. Value in fib. It should just go through. That's super weird. Can we just print value? What do we get when we print the value? Well, now the demo went badly. Okay, now we're getting the fib numbers here. Oh, I'm using fib, not value. I used the wrong variable name here. That's my bad. I want the value, string of the value, not the Fibonacci sequence itself. Sorry. I've not had enough coffee, or maybe too much coffee. It's hard to tell sometimes. There we go. So now we get a bunch of leading digits here. The 0, we don't really care about. That's fine. We can ignore that one. Apparently math people think Fibonacci starts with 0. I don't know any better, but I always assumed it started with 1. All right. So then to get the count of all of those, right, we can make a little dictionary for counts. And then for digit in from 1 to 9, we can take our counts, key of the digit, and we can either turn it into a string or leave it as an integer and then convert the digits back here. Either way, we need to deal with strings or we need to deal with integers here. So I think dealing with strings is probably easier here. We'll say, hey, it's happened 0 times for the counts. So now I'll get 1 to 9 here. And then for digit in digits, take my counts, key of the digit, plus equals 1. Right? They've all appeared 0 times, then loop through every digit in that digits list and add to the count. Right? I've seen that one here because I have all the keys, 1 to 9 in here. But I want to skip the first one here. So I'm going to go to start at 1. So I skip the leading 0 because we're never going to have leading zeros. Right? Otherwise, so we'll get rid of that one. Right? That's sure. It doesn't really matter. It's not gonna throw off our counts at all. And then when we're done, we can print this is our counts.keys, right? Will be the 1 to 9. We can print counts values. Right? That should be the number of times that each of those has occurred. Right? 1 to 9, and then we can see the count of them here. So if we go and graph those here with matplotlib, it'll look really pretty. So import matplotlib.pyplot as plt. And then PyCharm's like, hey, do you want to import this module? Yes, please. Install the package. That's why I like PyCharm. It does all the magic for us. It goes and installs the package. So we can call plot the count keys as the x, counts.keys as the x value, counts.values as the y value, and then plot.show. And again, we don't need to print those there. And we give that a run. Oh, it's still installing. Sorry. Kiwi solver, font tools, cycler, contour. Let's see, so many libraries. This is why, if you talk to your cybersecurity friends, stuff like this is risky, because who knows what packages we're installing, and hopefully no one screwed them up and put malicious software in there, because people have done that before. I know, right? Just cross your fingers. Yeah, and it's hard to scan all of it to know if you got good stuff or not. They call those supply chain attacks. Is the new hot thing in cybersecurity. So go talk to our profs who teach that. It's scary stuff. But we're not really doing anything interesting. So, and I don't have any Bitcoin on my computer, so probably fine. All right, now let's try and run it. 5, 1. Hey, we get our plot, right? The 1 to 9 on the X, occurrences on the Y. We didn't add any pretty labels or anything, but that was the idea with the lab. Does that make sense? All right, cool. I just had lots of questions, and this was just sort of an exercise in using these. We didn't get to the unit tests yet. We'll do some more unit tests. We'll practice that as well as we go. But all right, very fun. So that was the lab. Let me go commit that. Really got to clean this up here. Oh, did I not commit code from last time either? Goodness. Oh no, I changed a bunch of stuff. That's why for a demo. Hang on. Nope. Lab one. So you can commit just specific files if you want here. Yeah, I'm gonna just discard all those. There, I can push. All right, let's do new stuff. So let's do recursion. So this will be, is this week 2? Week 3? Like, because the first one was like half a week. We'll call this week 3 recursion. Is that okay? All right, so the simplest definition again for recursion is a function that calls itself. Okay, I think we talked about this briefly last time here. Again, a silly little function like countdown here that takes a number, and we can say we're going to print the number, and then if my number is greater than 0, let's call countdown of number minus 1. So it'll call itself and call itself and call itself and call itself and call itself. Eventually it'll stop when number is not greater than 0, right? It will stop running here. So if we call countdown, give it 10, right? We'll get 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, right? Like we'd expect here. So eventually it stops calling itself. So what we've done here is we've identified a base case. That's our technical term for recursive functions. The base case is when it's done. It doesn't have any more work to do. Right? So the base case is if the number's not greater than 0, right? We're done. So if we're not at the base case, what we've done then is we're making our function approach the base case. We're trying to get it closer to the point where we can stop, right? That's all. So we've got a base case, and then we simplify the problem till we get closer to the base case, right? So again, did we do the Fibonacci one last semester? Fibonacci is so fun. So let's define this as a bad fib here. A terrible way of doing it here. You want an nth digit of Fibonacci, right? So the base case, we know the first and second digit are 1, right? We just know what those are. So if my nth is less than or equal to 2, we're going to return a 1. Again, this will probably screw up if you ask for negative numbers, but again, it's not the end of the world right now. So our base case is we know nth is 2 or less, you've got to be the number 1. If it's not the base case, how do we get closer to it? Well, we can return bad fib of nth minus 1 plus bad fib of nth minus 2. Right? That's the mathematical definition. Take n minus 1, n minus 2, add them together. That's your Fibonacci number. So if we aren't at something that we know the answer to, let's simplify it. Let's get closer to something we know the answer to, right? So we can say, let's skip countdown for now. We can say for nth in range, let's do like the first 50 maybe. Let's print bad fib of nth. Oh, hang on, let's make this look a little prettier here. So let's do a formatted string. We want the nth and then the bad digit here. So we can see what the count is as we go here, right? There we go. So the first bunch go really quick here, right? And now it starts to slow down because my computer is literally adding the number 1 millions of times, right? Because the only thing it can do is get down to a 1, add that up, plus 1, plus 1, plus 1, plus 1, plus 1, plus 1, plus 1. So if we think about what's happening when we call this function here, right? I like drawing here because it's fun. Let's see. Oh, not the shepherd's pie recipe. New document. Right. Let me do my little draw tool here. So fib of 30. Oh goodness, that's terrible, but it's okay. That's a 30, right? Is fib of 29 plus fib of 28, right? And that 29 is 28 plus 27. And that 28 is 27 plus 26, right? On and on and on. So we've spawned millions of these calls, eventually getting down to 1, and we add 1 and 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 add 1. It's terribly inefficient here. Super simple though, right? This was the easiest thing in the world to write. It was 3 lines of code for Fibonacci, right? But it's terrible. And we don't need to use recursion to do that, right? A better fib, this is an iterative fib, we take an nth here, and we say our current nth is 1, and while my current nth does not equal nth here, right, let's keep on adding up here. So we've got a previous is 1, and current is 1, right? As long as we're not there yet, then the next is the previous plus the current, right? And then the current becomes the next value, or I'm sorry, the previous becomes the current, previous becomes the current, and then the next becomes the, no, current becomes the next, sorry. Current becomes the next. There we go. I can't think here. Not enough coffee, obviously. Okay, so figure out what the next value is, and then set previous current. Eventually, and then we'll take our current nth plus 1 here. So eventually we'll get to the nth value that we want here. This should probably be 2, right? Because 1 and 1. Doesn't equal. So I think we're going to get too far. Maybe we do need to start with 0. Maybe we start with 0. That's obnoxious. You can return the current. Let's see if iterative fib works here. So we'll call this with iterative fib. We broke something. What did I do? Oh, I never got to 0, right? Because we started at 1. Starts at 0. There it goes. Look how fast that one ran. 1, 1, 2, 3, 5. Okay. So I think we get the right values here, right? And that ran super fast because the computer can add up really quickly, right? Rather than adding 1, 1, 1, 1, 1, 1, 1, 1, 1. Right? We can add bigger numbers. That's all. So now this takes a little bit more code to make the loop here, right? We could also do it with recursion if you wanted here, so we could define a better recursive fib here that takes an nth. Now, what we need to do here is track the previous and track the current in a recursive manner. So the public function for better recursive fib just takes an nth here, and we can have this first call here. If it's 2 or less, just return a 1, right? We're done here. And then we can have a helper function, better recursive fib, that takes an nth, the current nth, the previous, and the current value. Right? So if you pass all of those things in, then we can say, okay, hey, cool. If the current nth is equal to the nth, we can return the current. Otherwise, right, we need to add those things together. So we'll return the better recursive fib of nth is still the same. The current nth goes up by 1. The previous is equal to the current, and the current is previous plus the current. Right? We're essentially doing the loop inside of a function call here, right? So when it runs here, it says, okay, hey, we're not at the nth we want here. So add 1 to your current nth. Your previous is now the current, and the next value, the new current, is the sum of the previous two. On and on and on. So we can take our better recursive fib, and this one will run a whole lot faster too, because we're not adding 1 every time. Oh goodness, we never returned here. Sorry. Return. Otherwise, return better recursive fib of nth. So then current is going to be what? 3, 1, and 1. Is that right? 2, 2, 1, and 1. Let's see if that's right. No, too many ones. So start at 2. Is that right? 1, 1. No, still too many. 1? 1, still too many. What do we do here? Oh, because this is less than or equal to 1. There we go. Current is 2. Current is 1. 1, 1, 2, 3. Okay, there we go. We got it. 1, 1, 2, 3, 5. We never started with 0. It's probably wrong, but again, it's just the illustration here. So this is using recursion as just a loop. Not really helpful, not a good use of recursion, because we could have just done it with this loop here, right? But this is something, when you have these sort of loops here, you can use recursion if you want in that manner. And it'll behave the same way. Now, this is actually less efficient because what happens behind the scenes is every time you call this function, Python has to track that. It has to track, hey, this function was called at this line, and here were the arguments. So it's storing all of these values in memory. So this is less memory efficient because behind the scenes, Python is storing nth of 2, here's the previous, here's the current. Nth of 3, here's the previous, here's the current. Nth of 4, here's the previous, here's the current. Nth of 5, here's the previous, here's the current. Right? So we've got this many more numbers we have to store in memory. So in terms of space complexity, this is not a good solution. Versus our iteration here just replaces them. We only need to store 3 integers, right? Our current, our next, and our previous, right? So we don't have to store as many integers. This uses less memory, uses less space here. So it's a better solution. But again, it's one way we can use recursion, right? Now, a better way that recursion is helpful is when we don't know when things are going to end, right? So if you think of your file system, right? If I wanted to go through and see every single file in a folder and all of its subfolders and all of its subfolders and all of its subfolders, I don't know how many folders you're going to have. So I could make a recursive function that says, okay, open that folder, give me everything inside of it. If it's a file, print out the file. If it's a folder, repeat, call recursively. Okay, open that folder, give me everything inside of it. If it's a file, print the file. If it's a folder, recurse. So like folder structures, operating system things are naturally recursive because it has that sort of hierarchy, and I don't know how many times we're going to have, right? I can't say, hey, there's only going to be 50 folders, so let's do this 50 times. Because some of you put folders inside of folders, inside of folders, inside of folders, inside of folders, inside of folders here. That's okay, right? We can do that. And that's nice and organized, right? We're already 7 folders in here, right before I even get into a project. So that sort of open-ended recursion is really helpful, right? And there are lots of things that have that sort of open-ended nature that we don't necessarily know when the end is, but our base case is, okay, I got to a file, print the file. The complex case, how we simplify it, is if it's a folder, open it. Right? Eventually, we'll get to the end of our folders here, okay? So another fun thing we can do is we can do what's called backtracking. So we're going to try something, and if it doesn't work, backtrack, go back a step, try the next step. Try it. If it doesn't work, go back. So we can solve mazes with backtracking. Small mazes, big mazes this fails on, but small mazes we can solve. So if I make a maze, which is a list of lists here, and we'll say, hey, a space is an open start, a start character, and then you can have open spaces here, and you can have walls. Right? So you can't walk through walls, you can walk in open spaces. There's our start. Let's do like a little 5x5 maze here. Right? So let me just put in everything open for now, and then we'll go add some walls in a second here. Right? Imagine these like rows and columns. Again, it's not really how they work, but it's easier for us to imagine rows and columns here. So let's put some walls in, right? So let's throw a wall here, a wall here, a wall there, maybe a wall over there, maybe one over here. I don't know. Give you a wall there, there. It's not a very interesting maze here, right? But we'll put a couple walls in. So going down is a dead end, right? We'll put another wall over this way. Going this way and up is a dead end. Going over this way, get to a dead end, right? Eventually you get to the end. So what we need to do is come up with what are the possible options we can do here, and we'll just try them. And eventually, if we get to a dead end, our base case is we have no more steps to go. We just undo, go back and try the next one. Or the base case is, hey, we got to the end and we solved it here. So what we can do is we can write a little class for a maze solver. So we can make a class for maze solver. Maze solver. That's all one word, right? I forget here. You can define an init here, given a maze. So you give me a maze, I'll go solve the maze. Right? So self.maze is the maze. Right? And then we can print the maze. I don't know if we just define ourselves as a string, maybe. That way you can print yourself is probably pretty easy here. We can return. Now, this is where you can do this, like the funny string concatenation stuff here. So we want every item, which is every row, turned into a string, all concatenated together here. Um, you know, Google will give you these sorts of things. Chatbots will give you these sort of things. We want a string of the row for row in self.maze here. And what do we want to do? We want to take all of those, so string dot. We want a new line character dot join. So we're going to take a new line character, join together the list of rows turned into strings here. I think that'll probably do here. So if we hand this maze to our maze solver, my solver is a maze solver. Given the maze here, we should be able to print the solver. And we're not doing any steps here, I just want to see if it prints out here. And we get the maze printed out, right? Every row is turned into a string, stick them together with new lines, so they all go down lines here, and we're good to go. So it's just a dumb little shortcut for doing that. It's not pretty, but it's not the end of the world. All right, so now we can show our steps. So then to go and solve here, we define a solve function. We need to know where to start and where we end. So we have to go find the starting character. If we want, we could just assume it's at 0, 0, or we could go and find it here, right? So we can have a start row is 0 and a start column is 0 for row index and range, the length of the self.maze, and for column index in range, length of self.maze of the row index. And in case the maze aren't perfect squares, right, there might be more columns than there are rows, not the end of the world here. If my self.maze at the row index, at the column index is equal to a start here, then my start row is the row index, and my start column is the column index. Go find the S here. And again, using an S here is probably pretty bad form, so it'd be nice in our class if we had some sort of constant here, like start is an S, right? So now I can use the word start here instead of the string literal S here. Self.start, use that start constant. Notice this one is defined outside of init here. We didn't get too much into that in our classes yet, but if it's defined without the self dot, it's a class level attribute. It's defined once at the class level and shared among all the instances here. Not every instance of maze solver needs to have its own variable for start here. So I can solve 50 mazes and only keep start once in memory. I don't need to copy it 50 times here, right, for each one to have. So we can use these class level variables here. Oh, it says I don't need my parentheses. We'll comment out those prints here, because that's not helpful for us. So eventually we'll find the start and end, or the start position here, right? Then, to go and solve then, I'm going to have a private helper function that goes and solves from a given location. Right, so I can track that here. So I can have a self-solve here, takes a row index and a column index. Right, so if my self.maze at the row index, at the column index, is equal to, we probably need an ending character here, right? So we have a end is an E. If we got to the end, then we're done. right? Our base case is we've solved it, so we'll just like print ourselves out. Maze is solved. If we didn't solve it, how do we get one step closer to solving it? Well, I'm going to try. You want to go up, down, left, right, or up, right, down, left, or whatever pattern? It doesn't matter. We just pick a pattern, right? We're going to try and solve the maze, right? How about up, down, left, right? So we're going to try up, and then we're going to try down, and then we're going to try left, and then we're going to try right. Okay. So to do that, we have to know, can you move to that position, right? Is that an available space to go in the maze here? So it's within bounds, right? It's a valid index, and it's open, right? Because you can't step on walls, right? So we need to go and have some little helper functions here. So we can call a try function if we want, right? Or we can have a helper function if you can go to. Lots of different ways to go. I like the is open here, or can move to. So define a can move to given a row index and a column index. Okay, so if 0 is less than the row index is less than the length of self.maze, right? Is it a valid row index, right? And then the same for column. And 0 is less than the column index, goodness, the backslash here. Sometimes it adds it for me, and sometimes it doesn't, and I'm sad. Is less than the length of the self.maze at the row index, right? Make sure that that column count of the row that we're in here, right, is valid, right? And self.maze at the row. So if they're valid, let's go see, is it a space? Is it open? And again, we should probably make a constant for that here, like open is just a space. And just avoiding these like magic strings here because it's easy to typo those here, right? If we have a constant, we can use that every time and there's no way I can typo it, right? So if it's valid row and it's a valid column and it's open, yes, I can go there. Now again, we don't need to be redundant. If it's true, return true, we can just say return, right? Save yourself a little bit of hassle here. We already have a true or false statement, just return that. It's true or false, right? So, okay, I can move to, right? So try up. So up is minus a row. So we can say, so if self dot can move to, row index -1, column index stays the same. If we can move there, let's move there. We'll recurse. We'll call self dot solve given the row index -1, the column index, right? And then down is the same thing, but row +1. +1, right? Left is row stays the same, column goes down by 1, right? Moving leftward a column, right? Oops. And then right is row stays the same, column goes up by 1. Right? And then we recurse. Try that, move, 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 right? Now what's going to happen though, really quickly here, so if we start here, can we go up? No, we can't go up. Can we go down? Yes, we go down. So we go to here and recurse, okay? Can we go up? No. Can we go down? Sure, let's go down. From here. Yeah. Well, our code says you can't step on an S. You can only step on an open space, right? So the way it's written now, no, you can't. But when we get to here, can you go up? Yes. Okay, so we go here, recurse. Can you go up? No. Can you go down? Yes. And we bounce back and forth, back and forth, back and forth. So we need a way to not step on a space we've already stepped on. So we want to leave a breadcrumb, right? Be like Hansel and Gretel. So what we can do is we can set a breadcrumb. So if we can go there, great. Let's put a breadcrumb down first. So we'll say self.maze at the row index, at the column index, and we'll mark it as like visited is a common term we use for that. So like a dot, maybe for our little breadcrumbs. So we'll have a visited is a dot, right? Again, just trying to use our constants here and be good here. Self.visited, right? Why does it not like that? Oh, it's not a private maze, sorry. Self.maze. There we go. Is visited. Then we'll try and go down. Now, having to do this every single time is a little bit annoying, right? So I'm glad you thought having the same code twice, you should feel bad about yourself. That's a pretty good rule of thumb, so we can turn that into a function. Again, this whole sort of like can move to, it's like try move. Right? So we can turn all that into a try to move here. So we'll try this. We'll say try move to a row and column. Right? So then we go back to an if. So if we can do it here, then we'll set the breadcrumb, right, from where we were moving, move to the new one and recurse. So we can change this one here. Now the problem with the try move, right, is I need to know where I was coming from. Because to set the breadcrumb, I need to know where I was coming from. So we have to add some more row index and column index. Column index. So we have a current row index, right? Current row index, and a current column index, and then a target row index, target, I can't spell, goodness, and a target column index. It gets a little bit wordy here. It's not the end of the world. You can bump it down if you want here. Right, so now is my target row index, target row index, and my target column index. Are those ones valid? Right? Then the target row index, right? If it is, then I can take my current row index and the current column index. I'm sorry, this one's target. Shoot, target, target. And the target's open, right? Then self.maze of the current row index and the current column index is self.visited, right? Mark it as visited, right? So if we can go to the target, mark the current spot as visited, and then recurse. So self.solve given the target row index and the target column index. So it'll mark it. Okay, I stepped there, right? So now all of these we can change here again. So we don't need to recurse, we just try, right? All of these just become tries, which is nice. Here, we'll copy paste. I'm zoomed in a little too far here, sorry. Try move to, what is it not like? Oh yeah, there's no colon here. We just try. Right? We try that one. We'll try down. So down is plus a row, right? Left is minus a column. And then right is plus a column. Right? We'll try it. We'll go there, put the breadcrumb down if we can, and recurse. Try it, put the breadcrumb down and recurse. Try it, put the breadcrumb down and recurse. So eventually what's going to happen, right? Excuse me. We go here, we put a breadcrumb down, we go down, put a breadcrumb down, go down, put a breadcrumb down, go down, put a breadcrumb down. We got to a dead end. It doesn't work here. So the code will come right back to where we left off and say, okay, well, I tried down. How about left? How about right? Nothing. It'll end, come back to here. Okay, well, I tried down. It didn't work. How about down? Or how about left? How about right? Nothing. It'll come back to here. Okay, well, I tried down. It didn't work. How about left? Nothing. How about right? It'll go to the right. Up, down, left, right. Okay, go right. Up, down, left, right. Up, down, left, right. Up, down, left, right. Okay, up. Oh, dead end. Can't go left, can't go right, can't go right, nothing. So we come back to here. Okay, we tried up, now let's try down. Up, down, left, right, up, down, left, right. And we'll try the whole sequence here. Eventually we'll get to the end here, and we'll solve their maze. Right, so it's just literally backtracking on itself. If it gets to where it can't go any further, right, the base case is there are no more moves to go. It just starts unwinding. So our base case is we either solved it or there's nothing left for us to do. Right, in that given position, there's no more maze to solve. Right? We reached a dead end. So if we give that a run here, so we made our maze solver, we printed it here, we'll call solver.solve, right? Our public solve function doesn't need any arguments. It'll go find the start itself here. Uh-oh. It did not solve the maze. Well, let's see what happens. So as every time we call solve, we'll call print of self here, just to see what our step is here. And then we'll probably print like a new line here just to give a little space as we go here. Is it not solving at all? I never called solve. There we go. So now we have the row and column, self.solve, bless you, given the start row and the start column. If we actually try and solve, now we should get a little further here. Again, so if we take out the prints for a second, still not solved. There we go. Now, okay, let's print every step of the way here and see what happens. It printed itself. Oh, we still have try move. Solve? No? All right, I'm a little confused. So let's put a breakpoint in and put it into debug mode. Totally on purpose here to practice showing you how to use the debugger. All right, so we got here, row is 0, it's column 0. So let's step into our code. Let's try move. So we're trying to move up here. Try move says, is the target row valid? -1. No, -1 is not valid. So we return false. Let's try down. Can we move 2? Target row is 1. That should be good. Target column is 0. That should be good. Is the target row, target column equal to open? Great, so let's keep on stepping. Uh-oh. Why didn't that do anything? Did I have this something messed up here? Row and column and equal to open. Right? Isn't that one equal to open? That should have been equal to open here. Is my indentation bad? Something funky here. What? Target row, target column, target row, target row, target column. It's open. Target row, target column. We're passing those right? Target row, target column. I think those looked good. Man, let me run it again. All right, step. So up is no good. Right, that one returned false. Let's try down. So we're step into, try down. So current row, current column 0. Current target row is 1, target column 0. So that should all be good here. So let's length of maze at the target row and target row index 1, 0 is open, opens a space. Step into. Didn't do it. All right, I'm a little confused. That's okay. Let's break this up a little bit more here then, because debugging a large statement's a little bit awkward sometimes. So we'll say is valid row is this one, and valid row is valid column is this one. So if is valid row and is valid column and is open will be this one. Now this one only works though if the row and column are valid. So we can't actually have this one separate because it might give us invalid indexing here. So I'm actually going to leave that one in. Right, so column and is open. Let me go do that stuff. Does that have to be indented one more? Let's try that for a second. Step into, valid row, valid column, those are valid. All right, move down. Valid row, valid column. Is valid column. Is invalid. Oh my goodness, 0 has to be valid, right? 0 less than or equal to. You guys let me have bad typos. Right, 0 is valid. All right, there we go. That was probably the bug there. Can we put that back then? Should we put it back or just leave it? All right. All right, let's see if it just runs then. Oh, okay, we're close. Now it crashes out on us here with invalid rows and columns. Oh, yeah, we can't use an invalid row index if that was invalid. Yeah, it's got to be all one line here because otherwise it's dumb. You want it to short circuit because as soon as it hits a false, it never tries the next thing here. 0. So if this is invalid, right, if this is false, it never tries to get an invalid row here. So it's helpful to have those be all in line like that. All right, let's try that again. Hey, okay, so now we're getting a maze here. There's a breadcrumb. 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 Oh, we never put one down for this last one here. I think Why didn't we put one there? Oh, because we never moved further than this one here. So maybe we put a breadcrumb down the first time we move. That might be a little bit nicer here. So we'll set ourselves as visited first. Every time we call solve. It's okay. All right, so then breadcrumb, pull this up a little more. Breadcrumb, breadcrumb, breadcrumb. We never marked the E as found here. So should we say, let's maybe have a self.solved is false. And eventually, if we solve ourselves, we'll say self.solved is true. So we don't print ourselves every step of the way here. We never print a solution. We never set solved as true here because we never said you could step on an E. Right? We have the base case, hey, if you got to an E, you're done, right? But we never said you can step on an end, right? So our try move to, it's open, right? Or it's the end, because you should be able to step on the end character here. So we could say, hey, is it open or is it the end? Yes, let's go step on the end here, right? And or those ones together. Now we should be able to solve it here, and now we get a solution. Because yes, we're solved. Because I was allowed to step on that end character. So you have to be a little bit careful. There's lots of little pieces. Yeah. No, because you have to say this one as well, right? When you compare, is it equal to? I don't think you can chain them together. Because if you just say or self.end, self.end is always true, right? If it's just all by itself, so you have to compare it to something else. Okay, we're getting there. So then if we want to mark every spot as visited here, we can actually save a little bit of code here, right? If we just mark every spot as visited that we step on, then we'll get our nice little path here. So we can cut that out. We can say, okay, every time we try and solve, we'll set our row index and column index to visited, right? Then we don't even need to give the currents, right? Because the only time we needed current was to mark it here, right? So we can make this function a little simpler again here by marking every step of the way. Right? And then that one still works. So it just recurses on solve. Do we really break it by doing that? Doesn't solve. Does that have to be tabbed in one more? No? What did I do wrong? My marking is visited. Oh, we marked the end as visited, and then we're no longer the end. Right? If we do this after the end check. As I said, hey, mark it as visited first. There we go. So we were marking our end as visited, which is probably bad. Now in this case, we marked the S as visited, which might also be bad. So we could check, hey, if our self.maze at the row index at the column index does not equal self.start, then mark it as visited. I'll make that a little bit cleaner. Oops, just a regular run here. Stop. Right now I don't override the start, and now I get my visited trail here, and I get the visited trail here on those dead ends, which is nice. So I don't need to print it to start here. We'll just run it, and it prints out the solution when we're done here, which is fun. Or we could just mark it as solved. We can get rid of the print here. Say, okay, it's done. And we can say, hey, if solver.solved, print solver. Right here, print the solution, if it was solvable. So it's possible we give it a maze that's not solvable, right? So if we put another X here, it's not solvable, it doesn't print. Maybe our else then is print unsolvable. We get that maze is no good, right? So if we printed it, right, we would see all those breadcrumbs as well. Kind of like dead end paths, but that's okay. Not solvable. Does that make a little bit of sense with this backtracking? So backtracking can be used to solve lots of different kinds of these like puzzles here. Lots of different ways we can do it here. Um, there's another fun one, which is called the 8 queens puzzle, or N queens here. So it's got a nice little Wikipedia page. Oh, I search N queens and it's using backtracking. Geek for geeks. Here's how you solve it with like, it doesn't even bring the Wikipedia page up because I was like, you want code, don't you? Here it is. Oh, 8 queens. Okay. The idea is, how do you put 8 queens on a chessboard in such a way that no queen threatens any other queen? For those of you who don't play chess, I'm sorry, you should learn. It's a good game. Queens can attack the row that they're in, the column that they're in, and their diagonals, right? So turns out there's 92 solutions here, but only so many unique ones that are not rotations or mirrors or some sort of nonsense like that here. And it works for n number of queens, which gets to be fun here. You can have larger boards or smaller boards up to, I think, at least 4, right? But look at that. There's 4 million possible arrangements here, but only 92 of them actually work, right? So brute force, doing it the dumb way, is backtracking. We're just going to try it. If it doesn't work, we're going to waste a bunch of time here. But again, the computer's pretty fast. So for 8, yes, it's fine. If you try and do like 16 queens, it will never finish, right? And that's okay. That's part of the fun here. So here's the fundamental solutions here without rotation. So just the 12 here. No 3 queens in a straight line. I don't even know what that means. How would they be in a straight line? Oh, like on some sort of weird like angle line? Okay, sure. All right. So we could solve n queens with backtracking, right? We just try it. If it doesn't work, undo, try the next step. Undo, try the next step. So this one has a little bit more interesting piece to it because there's an undo step. So on our piece here, when we were solving the maze, we said, hey, drop a breadcrumb. We never pick up after ourselves. We never clean up after ourselves. We just leave the breadcrumbs there like Hansel and Gretel, right? But with n queens, if I leave the queen there, but it's an invalid spot, it's going to screw up the rest of my stuff. So I have to clean up after myself. So this is an important step here that we're going to do. So let's do that in another, should we make another module for it? Call this n queens. So class n queens, find init, excuse me, that takes an n, we'll assume it's 8, but you can tell me otherwise here. So we'll have a self.board, then is a row of blanks here times n. We want that n times. Oh my goodness, there's some sort of shortcut. I forget what it is here. Um, times n. I think that'll give me the 8 spaces. Is that right? Times n again, like that. Maybe, let's see. I don't know. And we'll just steal that print board here from this one, or the string self.board. Well, hopefully it gives us the right number here. We'll make n queens. Here's an n queens. We'll print n queens. See if that works. Hey, 8 by 8. Look at that. That syntax is lovely, right? So this is 8 spaces in a list times 8 lists, 8 rows now, right? Sure. All right. So to solve then, we need to know a couple things. Right? We need to know if we're solved. Well, how do we know if we're solved or not? Well, we have n number of queens on the board. Well, if I need to know how many queens I have on the board, I should probably track that, right? So I can have a self dot number of queens starts at 0, right? And if my self dot number of queens is equal to self dot, or the length self dot board, right? That's probably easy for n, right? Or we could keep an n value here. Doesn't matter too much here. If we've done it, we don't need to do anything else. We'll print self, right? If we haven't, then let's try. Now, well, to try, do you want to go by rows or by columns? It's probably easier to go by rows, right? So all we're going to do is try putting a queen on the first row, right? Let's try it. So we'll say, now we're going to try every column in that row as we go here. So we can say for column index in range length of self.board, right? So if I'm 8, I'll get 0, 1, 2, 3, 4, 5, 6, 7. And that'll be my columns here. Now, the row I'm at is always going to be the number of queens that I have. When I have 0 queens, I'm at row 0. When I have 1 queen, I'm at row 1. When I have 2 queens, I'm at row 2. When I have 3 queens, I'm at row 3, right? So we can use that number of queens as our row number, essentially, here. So our quick little notation, we can say, hey, if we can place a queen, right, can place, and that's probably a helper function, can place queen at the self.number of queens at the column index, right? If we can do that, then we'll put a queen there and recurse. So we'll mark that, so self.board at the self.number of queens at the column index equals a q, or again, probably have like a queen here, right? Nice little value. Queen is q, open is a space, right? Self.queen. So mark queen, right? If we can place it, mark the queen, and then recurse. We'll call self.solve. Again, now we don't need to tell it anything else, right? Because we need to, or I'm sorry, we need to update our number of queens. So self.number of queens plus 1. We put a queen on the board. We have one more queen. Now recurse, right? Do it again, do it again, do it again. Now what has to happen though, we have to undo. So after we come back from this solve, if we're not done yet, we need to undo those steps. So we'll take our self number of queens minus 1, take the queen off the board, right? And put our board back to blank, right? Take the queen off the board. So this is the undo step. So self.open, right? So undo the things we just did here, and then we'll try the next column, and we'll try the next column, and we'll try the next column, we'll try the next column, we'll try the next column here, right? So the hard part here is defining, can we place the queen or not, right? So we can have a little helper function for that. Here, let's go, oh, self dot, can place queen, there we go. And let's add the method here, there we go, can place queen. So we need to know, can we put a queen at this row? Well, we know we always can, right? That one's pretty easy. Can we put a queen at this column? And then can we put a queen at this diagonal? And those are sort of the harder questions we have to look at here. And when you're thinking about diagonals for this n queens puzzle here, right, you've got forward diagonals going like upwards this way, and you've got downward diagonals, right, upward and downward here. So we never have to check behind us because we're only going row by row by row. No, hang on. Is it? No, we do have to check behind us. Shoot. So we have to check the diagonal behind us, the diagonal. We don't have to check the diagonal in front of us because we're going row by row by row, right? So we only need to check behind us going back and behind us going up, because we're always going row by row by row. So we're saving ourselves a little bit of hassle here. So we'll check the diagonal backwards and the diagonal forwards. So if, I don't know, so we'll just return. So we'll return self dot can place queen in column, right? And self dot can place queen, or check maybe, check column. Let's do that. If check column, column open. How about that? Column open given the column index. And is the diagonal backwards open? Now that one needs to know the row and the column, right? So it's the number of queens and the column index, right? And, oh my goodness, the backslash, self dot diagonal forwards open. Give the number of queens and the column index, right? So those three things, if those are true, then we're good to go, right? So let's, again, we'll have it, yes, write the function for me, please. Add the function, given a column index, right? So is the column open? So for row index in range, the length of self.board. If my self.board at the row index, at the column index, equals a queen, self.queen, return false, right? Invalid. Can't do it here. If we've checked every single location there and we didn't return false, we can return a true. Must be good here. Again, we could save a little bit of hassle if we wanted to, right? We only have to go upwards. Again, we don't need to check down as we're going here. It's like instead of the length of the board, we could go to the number of queens or something like that. It's fine, right? We'll check 8 more times than we need to. Sometimes it's probably okay. We'll leave a note here. Optimize for number of queens. Checking later. Is that okay? I'll leave it at a to do. Okay, that one's okay. So then the diagonal backwards. This one's a little bit trickier. Here, let's get the code generated for us here. Come on, give me my light bulb. So if we're going backwards, right, we need to make sure that the row index is valid and the column index is valid, right, and there's not a queen. So if we run into a queen before we hit an invalid row index or column index, it's no good. Right? If we've gotten all the way to one of those two indexes invalid here, then we're okay. So we can check while my, we want the row index or row index in range number of queens, right? Start at 0, 1, 2, 3. We want to start at where we are minus 1, right? If we're going backwards a row. So we'll go from that minus 1 down to 0, but we want to include 0, so like to negative 1. Stepping by negative 1. Oh goodness, that's really ugly here. I hate these for loops like that. I don't know. I guess that works here. That one's ugly. I don't like it. Let's say the row index to check is equal to my number of queens minus 1, right? And then my column index to check is equal to the column index. Now going backwards, right, is minus columns, minus 1. Column, look at that. I misspelled. And then while the row index is greater than 0 and the column index is greater than 0, right, as long as those are both good here, if my self.board at the row index to check, at the column index to check, is equal to a self.queen, we can return false. Not good here. Can't go there. If we didn't return, we'll take our row index to check, minus 1. We'll take our column index to check, minus 1. If we've gone through all of our rows and columns and one of them becomes invalid, we haven't returned a false, we can return true. That diagonal must be good. Right? Maybe. Did I lose you guys? Is this not fun anymore? Okay, it's still fun. All right, and then diagonal forwards, same idea, but now columns go plus 1, right? Instead of minus 1. So rows still go backwards here, but columns go plus 1. So my column then will be invalid when it is less than or the length of self.board, right? And we're going to keep on going by plus 1s. Eventually, it could go too far. Forwards. Look at that. It knows I misspelled it here. Forwards. That's awesome. I love when it does that. So then our start value has to change too then, right? So column plus 1 to start, right? Check the diagonal going forwards, right? We know we don't have queens below us here because we're going row by row by row by row. So we only need to check backwards and forwards here and in the column, right? All right, I'm sad this one's not optimized now. So let's start at 0 up to number of queens. So it's not number of queens. There we go. That was all we had to do, right? It'll check just that number of rows. So we have 0 queens. Nothing has to happen, right? When we have 2 queens, check row 0, row 1. That's all. All right. I think that's it. Right? We'll try and solve, undo, try and solve, undo, try and solve, undo, try and solve, undo. So this should print the first solution. Actually, I think this is going to print every solution here, right? So let's do another print here. Oh, it's the empty board, sorry. So let's call solve. So n queens dot solve. Uh-oh, didn't solve. Okay, that happens. Let's try and, we never called our recursive function here, did we? No, we did. We called solve. All right, I don't know. Let's put a breakpoint in. Put it in debug mode. All right, column index in range. So column 0. Can we place a queen at 0, 0? That one's open. Column's open. Diagonal's open. We'd expect. Diagonal forwards. Is that one open? True. Open. Good. So we can place. So we're going to put a queen down. Add 1 to the queens. Recurse. Right now queens is 1. Uh-oh. Oh, okay. This syntax here is bad. I don't know if you saw there, it put a queen on every single row when I put it on one row. It's the same list. Yeah, so, okay. We'll fix that here. We'll just make this a list and then for row in range n self.board.append new list of space times n. I think that'll work for us. There we go. Yay, that worked for us. So if you don't make bad copies here, life is good. So first solution. Uh-oh. That doesn't look like a solution here. I got a queen here and a queen here. That shouldn't happen. Thinks it's solved, but it's not solved. All right. So why didn't that pick it up here? So if we can put diagonal backwards, diagonal forwards, given the row and column, right, if we can place a queen, so it should have done the diagonal backwards, right? Number of queens -1 should have been 0. Column -1 should have been 0. So from 1, 1 should have been 0, 0. 0 is valid. Oh, less than or equal to. Did it again, you guys. 0 is a valid index. You got to slap me. And then one more over here. Let's try that. All right, how's this first solution look now? That one looks better, I think. Right? No queens in that row, no queens in that row, one row, like, or the columns, right? Columns are good, rows are good, and then diagonals. Diagonal, 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 diagonal. Diagonal, that one's good. Diagonal, 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 that one's good. Diagonal, 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 that one's good. I think we found solutions here. So this is pretty quick to solve with recursion, right? We just do it and try. Without recursion, we have to be managing all of these states and tracking them everywhere. You can do it, we don't know how yet, because we haven't talked about a stack. But we can build our own stack here to track these things if we wanted here, and that's where you get some of those Google solutions, right? And you can start seeing without recursion. Let's even ask it here. Let's go to UMGPT for fun. Why not? Let's ask it here. So write an 8 queens puzzle solver in Python. Let's see how it compares to my solution here. This is way faster, I think. There it goes. If row is n, right, we did it. Otherwise, for every column, if it's safe, append the column, solve row plus 1, solutions. Okay, I don't know why it's tracking the solutions thing, but that's fine. If it's safe, right? If the column is valid, I is a column. Oh, it's probably close here. I don't know what this one's doing, but it's probably pretty similar. Oh yeah. Oh, it gives you total solutions as well, right? Oh, so you have a list of solutions. So it'll give you this list here, which is nice. That's all. So it's giving you every possible solution. I'm printing everyone. My function's calling print. This one doesn't call print here. And look at that. Print solutions for number of solutions and enumerate your solutions. Solution number. Print the solution. Print a space joined q. If I is r, else a dot for I in range. Like some of this code is ugly that chatbots give you, right? Like I feel like I could probably read it if we tried a little harder, but that's kind of ugly. Mine's a little ugly too, but I feel like my variable names are better than I and R, right? That's why I hate I's and R's. Okay, but that's good, right? So great. And then write it without recursion. Recursion. Yeah, the backtracking solution. So uses a stack to keep track of, iteratively tries. Oh my goodness, look at this. Look at that. While true, you have to use a stack, keep the board, keep the solutions here. if it's good, if we found a safe one, do the backtracking thing. Oh my goodness. That's nasty, right? But it doesn't use recursion. Yay. So again, we don't know what stacks really are quite yet. We'll get there. But you can. That's sort of the idea with that one. Does that make sense? All right. That was our start of recursion. We'll come back on Thursday, talk more about recursion, and we'll have a lab the following Tuesday on recursion. Very exciting. And then we'll do some unit testing to practice that as well. Or if you want more unit test practice, you can do that Thursday too. Just holler at me, okay? Great. Thanks so much. We'll see you Thursday.